So welcome to the Winds and Currents webinar. Today, Fabrice Ardhuin from Ifremer is going to speak about waves, phase speed, and Doppler velocities. Take it away, Fabrice.
All right, thank you. Thank you, everybody. So it's a pleasure to be here. I'm sorry I haven't made much more progress in the last months, but okay, that's essentially I'll try to explain the consequences of what Ernesto was showing 2 weeks ago or something like that. So this work is done with some help with Frédéric Douguier, is working a lot on different simulators for different instruments, and Samuel Osina is an engineer working with us for the project. And I'm actually affiliated with a laboratory for ocean physics and satellite remote sensing, which happens to be a joint research institute with Ifremer. So yeah, you can call me Ifremer, but for French people, it's actually a more complex situation than that. I started with this picture here, which is showing the degree of linear polarization in optical imagery of the sea surface for conditions with a wind speed of around centimeter per second. Just introduce what the actual ocean looks like at small scale. So the field of view is about 2 meters across, and you can see waves down to maybe 1 centimeter, maybe a little less. The 1 centimeter here will be relevant when we actually start talking about what ODYSEA is measuring at the surface, because it's supposed to be sensitive to stuff at 4 millimeter wavelengths. So you can probably see some roughness at that kind of scale, which looks like maybe some kind of gravity capillary waves all over the place, not just at the crest of long waves, but also pretty much in the middle here too. So that will be what I'm going to try to get to. All right, so so I'll start with my conclusions because I'm not sure how long it is going to take me to go through all of this. So basically, all radar measurements of current in quotes are actually a measurement, measure geophysical quantity. Use a measure of geophysical quantity that is a combination of wind wave phase speeds. So we basically see the motion of the surface only through the motion of surface waves. And for practical applications, you may want to break this velocity into a current part and a wave part, or a wind part, whatever you want to call it for the second part. And basically, the average phase speed of the ocean is a sum of a current and a wave-induced velocity. And the big difficulty in understanding what we're measuring is to re-understand what this averaging is. And the averaging actually depends a lot on which system you use. So whether you use a different frequency for the radar or if you use different angle of observation. So it turns out that the incidence angle is actually going to be a very important thing. So at near-nadir angles, we find that velocities contain a current which is roughly measured at half meter depth, or average over 1 meter if you want. And the wave contribution is about 2 meters per second. So it's pretty large, much larger than the current in general. And you can write it as a ratio of a mean square velocity and the mean square slope, and that actually changes as a function of radar frequency. And if you want to correlate that with the wind only, you still will have a pretty big residual, which is about 0.6 meter per second. This is why on SKIM we went for a measurement of the wave spectrum on top of just the Doppler velocity. So you can use a wave spectrum information to reduce that residual. In the case of DopplerScatt and ODYSEA, you can make an argument that the depth of measurements is typically around half of that, and I'll explain that. And the order of magnitude that was shown by Ernesto is a typical 0.7 meter per second wave-induced velocity. Probably that's 0.7 meter per second correlates well with the wind, but if it actually scale with the Stokes drift, you can expect a 0.06 meter per second residual. For which, if you want to go to high accuracy, you may want to use ancillary data or something like that, because that kind of error, it's not a random error that won't actually completely go away when you do averaging. So that's something to be maybe worried about. All right, so how do I come with these conclusions? This is what I'm going to try to walk you through now. So as I was saying, radar targets and how we see the ocean is really a function not just the ocean, but also the properties of the radar and the measurement geometry. So for those of you that never really thought too much about that, so if you have a radar looking along a line of sight at the ocean, it's going to hit the surface at some point with an angle, which we call the incidence angle, which is the direction between the line of sight and the normal to the geoid, so local vertical. Of course, the surface is not flat, otherwise you don't get any return back to the radar. And we'll walk you through different systems, starting with HF radars, which maybe most people are not familiar with. Then a little bit about near-nadir incidence, and then going to ODYSEA And other systems like SEASTAR or Harmony would be somewhere in between because of their in-between incidence angles. All right. Yeah, so we have to think about the targets of the ocean and what are the targets, what's making the signal. So basically the sea is flat, there's no wind, there's no backscatter, so there's no measurement. But fortunately the sea is not flat, we get this kind of ocean features. And what we find is that the measurement of the phase shift that you get into radar echoes, and you get the same physical measurement, whether using a pulse pair measurement or an ATI measurement, so interferometric SAR, and that was shown by, there was a paper by, what's his name? Our friend from Miami. Cheers. All right, back to me. So using various systems and showing that you can actually have equivalent measurements. And so so you have this line of sight velocity that contains essentially a combination of all the echoes from all the targets on the surface. And so you can think about the targets as a piece of the ocean surface that can be considered independent of one another. So you have different targets and they collectively will give you the signal. So essentially we can think about two types of targets. So we have either specular facets, and for ODYSEA with 55-degree angle, these are very steep slopes on the ocean. You don't have very many of these, and likely that would be associated with breaking waves. And the other more common targets is probably Bragg waves. And so I put waves in quotes because this is basically any roughness that has wavelengths that will resonate with the radar wavelength. So that means that wavelength lambda b equals to the electromagnetic wavelength of 2 times the sine of the incidence angle. So these they don't have to be free waves, propagating waves. They can be just harmonics or whatever roughness you have on the surface. All right, so then you can think about the surface as a Fourier sum, and there's no assumption regard for that. Just do FFT of the surface elevation, and that would give you a motion of the surface in time. That would take this expression, and the reason why I'm emphasizing this is that basically any motion at the surface will have this omega, so the radiant frequency times the amplitude of the surface elevation coming in, and how the currents come into our picture is that the currents change the dispersion relation on the surface, and so for linear capillary waves, that would be this omega equals square root of gk blah 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 plus k dot u, where u is a current. And so if you have a current vector, which is actually not uniform over the depth, then you have a u here that also a function of the wave number k by the current profile, and that also contains nonlinear wave effects, and you can think of it as a filtered Stokes drift, and there's some various papers that have discussed this before. So my current here would then include Stokes drift for practical purposes. Okay, so that's all up here. Let's minimize my window here, right? And so one way to think about that is that the average velocity of the surface is the velocity of the scatterers times their brightness, which is this lambda function here, and this all normalized by the sum of the brightness. And that was essentially how Bertrand Chaperon wrote this up a couple of years back. So we can look at different systems. So yeah, so the first one, which is relatively simple, is HF radars. So they usually work at HF, VHF frequencies, so 2 to 50 megahertz, sending radar waves horizontally, so grazing angle incidence. And in that case, the only targets to get are Bragg waves. There's for typical range resolution. So when you work at this kind of frequency, it's hard to get your authorization frequency to be broader than 100 kilohertz because the people that manage the bandwidth, they hate to give you that much. So very often you limit to like maybe 50 kilohertz, but okay. If you have 100 kilohertz, you have a resolution which is around 1.5 kilometers, right? So that's actually not super, that's what you get, right? And the fact that you can actually listen to the ocean and send pulses throughout time, you can actually make a Fourier analysis of your time signals and get what's called Doppler spectrum. So essentially a power spectrum of the echoes as a function of the frequency. And then you get this kind of pattern where you have peaks here, which are related to the dominant scattering mechanism, which is Bragg scattering. and you have first order peaks and the second order peaks. I won't talk about it, but basically you get echoes at all the frequencies, and they are dominated by Bragg waves, which are going towards you or away from you. So waves at a very well-chosen wavelengths that are resonant with the radar wavelengths. Now, if you cannot make a Doppler spectrum, as is the case with ODYSEA, you would get a mixture of all these velocities. And just to give you some rough ideas, so because you have stuff going away from you and towards you, in this case, there's only a 5 dB difference between the two peaks. So the mixture of the two will have velocity which is 0.5 times the Bragg velocity. If one peak dominates more, you can actually get to close to 99% of the Bragg velocity. But in general, you have a mixture of both velocities, and this is why the ODYSEA GMF may look how it looks. And so it actually is pretty important to know what is the relative magnitude of waves in opposite direction. We started to get some good ideas about that down to wavelengths of, let's say, 0.5 meter or so. We have actually a paper in press now with JGR discussing some of that. At Ka bands, resonant frequency wavelengths, I was saying 4 millimeters for ODYSEA. I don't think we have any clue what is this directional distribution. So there's some uncertainty there. So possibly there's actually a little bit of energy going back opposite to the wind that could change a little bit that Bragg velocity magnitude. All right, so the one thing we know about HF radars is that if the current is not uniform, so the phase speeds is a depth weighted mean of the current, and the weighting profile is these kind of red lines here on the left. So if you imagine a situation with a mixed layer depth with a current U here going from 0.5 meter per second to 0 below 10 meter depths. And so if you imagine you're sampling your ocean with different wavelengths, so 10, 12 meters, 24 meters, and 60 meters, you would basically get at for this mixed layer depth of 10 meters, 3 different values for the different wavelengths. And now if you change the mixed layer depths, you get different magnitudes of the current. And if you had a linear shear instead of that, you could actually show that the current you're measuring with your radar is a current at the depths, which is the Bragg wavelengths divided by 4 pi. So 4 pi is about 12. So, for 12 megahertz radar, you're down to about 1 meter. So that's, it's very hard to say that the radar is measuring at a given depth, because it's not. It's actually giving you a depth weighted average of the current, which, for simple cases like linear shear is a simple number. But in general, if you actually make this kind of step profile, it's going to be something a bit different. And that's a very general property for all radar sampling, because we always have this kind of averaging of the phase speeds seen by the radar. All right, so a few words about near-nadir incidence angles. So first of all, the first question we had, so why would you actually measure the horizontal current by looking almost vertically? That makes no sense. Well, not quite. And I'm just borrowing this picture from a paper by Ernesto from 2018, in which he was showing the sensitivity, or rather the error you make on the measurements as a function of incidence angle. And the fact that when you're actually measuring near to vertical, you typically have a brighter return, a stronger radar return. And so that actually helps you in getting a more accurate current measurements. So if you want to get the most accurate current measurement with Doppler scatterometer, you actually work best at around 10-degree incidence angle, which is what we chose for SKIM. The good thing is that you can make a very cheap instrument for that, because you don't need to use so much power. And the bad thing is that, well, of course, if you look almost straight down, the SWOT is actually much more narrow than it is at higher incidence angles, like 55 degrees for ODYSEA, which is the main reason for ODYSEA and DopplerScatt to work with 55 degrees is to actually maximize the SWOT widths. There's another caveat when you look at near-nadir incidence, is that the wave contribution to the measurements is actually larger. And I'll explain that right now. So for near incidence angles, we can actually have a very nice theory for what should be the phase speed of the different waves contributing to the signal. And I'm not going to go through all the details, and this slide is already pretty much too busy, but it's all discussed in the paper by Nguyen et al. 2018. what we find is that typically the geophysical Doppler is the ratio of the mean slope velocity and the mean square slope. And the mean slope velocity is basically a weighted sum of the phase speed of the different wave components multiplied by their slope spectrum, right? So that is what it looks like. So it's some integral over the spectrum. So we have the spectral density of the surface elevation here, the wave spectrum, times the phase speed, and then times some wave numbers and some directions and all that stuff. The phase speed contains, as I said before, the intrinsic phase speed of the waves, so that the phase speed it would have without the current plus the current, right? So you get a sum of the current components, this UCD, and then the other wave Doppler component. And in this case, you can actually find that the wave Doppler component is roughly proportional to the Stokes wave times some coefficient G. And this coefficient G is about 30 in general. And that depends on the wave radar frequency and the incidence angle. So yeah, I'm going to skip that and go direct to the results. We actually demonstrated that with some airborne data. So we had this offshore Brest. So we had an airplane flying with a side-looking radar measuring at 12 degrees incidence angle, and and we flew in a star pattern. So we flew one way and then the other way, looking at the ocean surface. You can see one line is in red and the other line is in blue. It means that we're actually measuring opposite velocities as we go one way or the other way, looking on the side of the airplane. And then as we sample different azimuths, you can see that at some point the velocity goes to almost zero. And basically from the azimuthal variation of this velocity, you can actually fit a vector of the current measurement, or sorry, of the geophysical Doppler measurement with this UGD, which is what we measure. And then we retrieve the current by subtracting from this guy, the geophysical Doppler, theoretical wave Doppler estimated from the wave spectrum and the theory from Frédéric Nouguier, so the paper from 2018. And when you do this subtraction, so you can see that you have this pretty big number, which is something like 3 meters per second, and you have a vector you have to subtract, which is about 2 meters per second, and then you end up within the ballpark of the other measurements, including HF radar, some SVP drifters, and some Carthay drifters. So that's how we demonstrated that you could actually measure surface currents from an airplane flying a radar and looking at 12 degrees incidence angle. And the idea was to then take that to space. And that was a SKIM proposal, which didn't get funded, but basically it was demonstrated like that. One small detail is that when you actually think about the weighting of these phase velocities by the slope spectrum, this is the average slope spectrum of surface elevation of the ocean in blue. So you typically have many scales in it, and a lot of the slopes actually correspond to stuff longer than 10 meters, but you also have a lot of energy or variance in the slopes at scales smaller than 10 meters. And so when you do the average of all that, you find that the effective depth is about 1 meter, which is very close to what we get with the HF radar. And it actually varies seasonally. It varies a little bit if you have a storm or no storm, because the shape of the spectrum would change. But it doesn't, it's within, let's say, plus minus 10% of this 1 meter average. Okay, so now if we go from near-nadir to 55 degrees in angles, what happens? So basically at 55 degrees, we don't have so much specular reflection because there's very few facets at the surface that have a slope of 55 degrees. So probably you get some breaking fronts, like this piece of the wave here, which is probably steep enough to be specular reflector. But then the other contributor to have to the signal is some Bragg scattering. So any roughness which will have a wavelength of 4 millimeters would contribute something. So it can actually be a freely propagating Bragg waves with that wavelength. So that would be a capillary wave, or it can also be some harmonics of longer waves or whatever is on the surface that have this kind of scale. And so that's very much detailed in the paper by Rodriguez et al. 2018, and there's some nice discussion also in Jaroski et al. Remote sensing 2019. And so the big question for the Doppler and the velocity we're measuring is how does this 4 millimeter roughness actually moves on the surface? So I was saying, maybe there's 3 waves in that case. We know what should be their velocities, and then we can say that what we're measuring as a phase speed is a current plus the free linear wave theory Bragg wave velocity. Or what happens is actually we have many different effects of longer waves. So in his paper, in their paper, Rodriguez et al. Actually discuss especially the effects of Doppler shift and hydrodynamic modulation. There may be some other effects that could be relevant, especially the fact that when you're small waves riding on top of larger waves, you are going to feel a gravity which is not the constant Earth gravity, but some apparent gravity which contains acceleration of the motion up and down. I'm sure that anybody's been on a ship have felt that. When you feel your stomach moving up and down as you go right on the crest of the wave. Well, that's this apparent gravity that you're feeling. Of course, if you're going to further and further towards capillary waves, the gravity doesn't matter too much. But as you're close to the capillary gravity threshold regime, then there's still a little bit of this gravity modulation. The other thing is that the airflow above the waves is also modified by the presence of the waves, and so we also get some aerodynamic modulation. So the apparent wind is actually modified by the wave motion. So many different things we don't quite know much about, and so hopefully one day we'll have a full answer to all that. But in the meantime, we can start with simple things. The one thing which is robust and the people have been playing since a long time, Thomson and with it, some papers from the 70s already, is the effect of the tilts. So the fact that when you're sampling the surface, so imagine you have some long waves here, pictured with this black line. And on top of that, you have short waves, so they are not to scale here, of course. These are meters, and imagine some short waves on top of that. If the short waves don't feel the long waves at all, they have a constant amplitude and they get the same short waves all over the place. But what happens is that because we have a collection of waves with all sorts of different wavelengths, and we have actually a spectrum of waves, the waves that have the right Bragg scattering wavelengths, they will actually be different at different places along the long wave profile. And the main reason is that the local incidence angle, taking into account the long wave slope, is going to be different, and so the sine theta you get in the lambda in the Bragg resonant condition will actually select waves that are longer when the local incidence angle is larger and shorter in the other way. And because longer waves have a larger energy because of the shape of the wave spectrum, typically indicated like k⁻⁴, that will actually contribute a very different magnitude of the Bragg waves amplitude along the long wave profile. So to make a long story short, basically you have a wave Doppler velocity, which you can write as some average Bragg velocity plus some effect of the tilting of the long waves and this change of the Bragg amplitude. And so we've been playing with the most simple, just this very simple modulation effect. So we take ocean surface that was discretized with a resolution of 3 meters. We have facets that are 3 meters long, and we do that over a footprint, which is a footprint of ODYSEA. So I don't remember exactly in the calculation what was chosen, but it's something around 30 by 30 kilometers that was used actually in this in the simulation to make sure we have the entire footprint and even beyond the going to more than just the half widths. And what was done here is to actually compute the Bragg, the Doppler velocity from either the full simulation or freezing the short waves or freezing the long waves. And so if you freeze the short waves, in that case, you only have the effect of the long waves in yellow. So there's no Bragg velocity of the short waves. It's just that the velocity, orbital velocities of the long waves are correlated with sigma naught, and that will give you some average Doppler velocity. The effect of the short waves is essentially just their Bragg velocity, intrinsic velocity. So the theoretical Bragg velocity here is this dashed blue line here. And you have almost a top hat function if you have waves in only one direction. So because there's actually a transition between waves and some energy in the opposite direction, you get some smooth transition between these minus 31 centimeter per second and plus 31 centimeter per second. And basically what the model numerical simulation shows us is that we actually understand what's going on. It's a very simple simulation in which we only take into account the tilting effect to give the local backscatter and velocity. and so we get something which is plus minus 60 centimeters per second. So that's a very simple thing, and this is basically what can compare to empirical simulations. So what you have here is for 4 meters per second, 7 meters per second, and 10 meters per second winds as a function of the azimuth direction. So 0 here is taking the Ernesto et al. 2018 convention, if I got it right. So 0 is supposed to be downwind. And so we mean that the velocity of these waves propagate in the same direction as the wind. And so velocity would be positive here for 0. Which would correspond to a negative Doppler shift, but okay, so there's a minus sign and all that, don't worry. The yellow line is the empirical GMF that was fitted on platform data by Ardhuin et al. So we call that the KDOP model. And basically, the simple tilt gives you some order of magnitude, and so Ernesto actually did the same calculation in his 2018 paper, so no big surprise there. And what you can see comparing the top panel to the bottom, so the bottom is, I'm not sure which flavor of the SMOD data was used here and which version of the plot I used from Ernesto, but it's basically some of the plots generated by Ernesto using some SMOD data, either from last year or the previous experiments. So what you can see is that 4 meters per second, the SMOD data actually gives you a much higher GMF velocity than KDOP, and that means that essentially there's a lot of things missing in the very simple tilt model here. It's actually almost right there for 70 per second, and especially the top hatish kind of shape, which is probably a signature of the Bragg waves without the tilt, is there. I'm not too sure about the double maxima, and so Ernesto had some nice theory for that, but we can discuss that later. And at higher wind speeds, it seems that there's a lower magnitude of this empirical GMF. Whereas in our very simple model, we actually get an increasing effect. Basically, you get more energy in the long waves, more tilting, and so the higher the wind speed, and the more you get signals and Doppler shift. So that's what's happening in our very simple model, which is actually contrasting very much with the observation. So the question, of course, after that is, okay, what's missing? And so we can take the story that Ernesto was telling about, okay, what was possibly missing in there. So if you read the wave Doppler velocity as also, the first term here is a tilting model that I was showing you before, which, so in this plot here, you have this wave Doppler velocity. So yeah, in Ernesto is called VS, in my thing it's called UWD. So sorry for the mixture of notations. So the blue model is just a tilt I was just discussing before. And then what Ernesto has been fitting is actually two functions. So one would be corresponding to this first term here. It's whatever change in the magnitude of the Bragg waves that would be correlated with the horizontal velocity of the waves, so the orbital velocity u. So if you have some correlation there, that will give you some coefficient mr times the some expression from the wave spectrum. It turns out that this expression from the wave spectrum is actually the Stokes drift. So any change you make in this delta B here and delta B there by having a linear modulation will give you a term in the end in the wave Doppler that is proportional to the Stokes drift. Okay, so one is in phase with the amplitudes of the waves and the orbital velocities, and the other one is out of phase, so it's actually in phase with the vertical velocities. So we could discuss what causes which. I just make a short note that if you actually have some variation of the acceleration going through the Bragg phase speed, that will typically give you a change in the Bragg phase speed, also correlated or anti-correlated with the orbital velocity here. But the important thing here, even though we don't understand what's behind this, is that if you write it with this linear modulation, you have something which ends up being proportional to the Stokes drift. Things will probably be a bit different when you actually explicitly represent breaking waves. because they don't have any good reason to scale with the Stokes drift, and maybe that will actually be more representative of the magnitude of the wave spectrum or saturation spectrum in each direction. So that might be one possibility for explaining this double maximum at two different directions, because the actual spectrum is bimodal and may do something like that. But okay, if we put that under the carpet for now and just accept that maybe we have some correction proportional to the Stokes drift, then we have to think, we can start thinking about what it is that we're measuring and how much is it actually correct to use a GMF based on the wind only. So right now the algorithm that is used for DopplerScatt to retrieve the current is to subtract this wave-induced Doppler by having this empirical GMF from which using the wind speed and wind direction. So essentially the curves I was showing you here. So basically the blue line. These are actually were obtained by collocating DopplerScatt measurements with in situ data and removing the current to find the wave-induced Doppler. Of course, when you want to get the current, you do it the inverse way. So you compute what should be the wave Doppler, and you remove it to get the current. And typically you do that at all the points where you don't have the in situ measurements. And okay, so when you do this correction using this GMF, you may be worrying a little bit that if what we just said before is correct, the fact that the roughly half of the Doppler scales with the Stokes drift, then you actually want to think, okay, how much is a Stokes drift related to the wind, and how big is the residual? And so for that, there's several ways you can start thinking about it. So what I started doing some time ago is just take a look at buoy data. And so here's an example looking at my favorite ocean buoy, which is a CDIP station 166, which is collocated with station Papaya in North Pacific. And I thank Megan Cronin for all the wind measurements and current measurements from the buoy, and Jim Thompson for the wave spectra. And so this was actually you 7 years of data. I could have used even longer, but okay, that's a start. And so what I did is to average data over 1 hour records. So I collocate the wind measurements in time with the wave spectra and compute the Stokes drift from the wave spectrum using the directional spectrum, not just the heat spectrum. So there's some directionality of the waves included in there. And so if you actually look at a given wind speed, what you will find is that there's a variability in Stokes drift. It's not huge because the wind, wave height, and Stokes drift are all correlated. But you can look at you can stratify the data as a function of wind speed and wave height, and you can see that for a given wind speed, if you move, let's say, okay, let's look at 70 meters per second, the typical average wind speed over the ocean, the Stokes drift will increase from somewhere around 0.07 centimeters per second for a wave height of 1.5 meters, and it will increase to maybe 0.1 meter per second. For a wave height of something around 3 meters or so, right? So that's all the contours here are every half a meter per second, half a meter for wave height. And so basically there is some variability in the Stokes drift, which is not noise. It's actually some geophysical effect that the waves are not in equilibrium with the wind. There's some change in the sea state that will change the Stokes drift, and the residual. The difference between the Stokes drift and the average Stokes drift for a given wind speed is about 2 centimeters per second on average. It's actually increased a little bit for higher winds and higher Stokes drift. And if you look at how the GMF scales with Stokes drift in the case of DopplerScatt currents, that will typically give you a factor of 3, and that's something which gives you then a residual error of about 6 centimeters per second in the retrieved current. So at some point, Ernesto was saying, well, it's very likely that all of that is large-scale biases, and it's quite possible, and because typically the part of the sea state which doesn't correlate well with the wind is going to be more the longer waves, and the long waves are typically variations are large-scale. But at the same time, we've shown before with a paper with Sarah Gillies co-author that waves actually also correlate with the currents, and so that study will have to be redone again by checking on specific effects of small-scale currents on the wave field and Stokes drift, and that's probably something that would be a nice thing to do with SMOD data. So I don't have much more than that. It's just to give you some example of typical maps of Stokes drift and currents over the Gulf Stream. The contours on the top plot are the wind speed contours. Of course, the wind's not uniform, but it's typically large scale variations, and all the small scale you see in Stokes drift is typically actually caused by the local currents. And these modulation small scale would be of the order of a couple of centimeters per second, maybe 1 or 2 centimeters per second. And there's something interesting that could be done, maybe to try to correct for that or not. So yeah, go back to my conclusions. So yeah, the way we can think about how radar measure currents is actually through a combination of wind wave phase speeds. Of course, it's practical for application to try to break it up into current plus something else, but really the reason why they're actually combined is that they are combined through the phase speed of the waves that are our targets. At near-nadir, we believe we have a pretty good handle of what's going on, and that allows us to say something about what is actually the depth at which we're measuring. So the average depth will be 0.5 meters depth, and so averaging over twice that if you want to make it a 1 meter layer. But the big difficulty at near-nadir velocities, and that goes all the way to 20-30 degrees from nadir, is that you have a really large contribution of the waves to the signal. And there's actually good approximation of that velocity, which is this mean square velocity divided by the mean square slope. And that's a function of incidence angle and radar frequency. And so typically, if you only have wind measurements to correct for that, essentially you're trying to correlate this mean slope velocity or Stokes drift to the wind, and that will end up with a residual error of around 0.5 meter per second. So you need more than just the wind to correct for that. So we typically, ideally, you would like to have a full wave spectrum down to wavelengths of about 30 meters or so. In practice, you're very often constrained by measurement issues. So, SEASTAR has some capability to measure wave spectra. We still have figuring out exactly how far we can go toward shorter wavelengths, but that's something that's going to be important. And so, in the case of DopplerScatt and ODYSEA, from the DMF that Ernesto was showing, obtained from SMOD, so you can make the argument that because you have half Bragg velocity and half modulation effect, so it's going to be half really super surface stuff and half a little lower. So on average, it's going to be maybe more correlated with a current that's half the depth of what we get at near-nadir, and maybe more interesting. Because you get this possibly correlation with the Stokes drift, you can expect that it's not just the wind, but also the seated would be important. And you may expect of the order of, let's say, I don't know, 5-6 centimeter per second residual error if you only correct from the wind speed. So, of course, this is just the first steps of working with DopplerScatt data. I guess maybe later on we'll have models that can compute wave spectra over these currents and maybe iterate to get a more refined estimate, but that's something we need to think about more in the future. So that's pretty much all I have. Maybe I was a bit too fast on some things, so let me know.
And thank you, Fabrice. This was great. And we'll open the floor to questions. And okay, Ernesto has raised his hand, so we'll let Ernesto go first.
Really nice talk, Fabrice, and really nice summary. I had a couple of questions for you, maybe too many, so some of them we can take offline. But the two main ones that I guess that impact ODYSEA is in your modeling that you're doing right now. It seems like you could additionally include bound capillary waves, which have been shown for backscatter cross section for winds to be potential significant contributor. So I was wondering if you have longer term ideas as to how to do that. And the second question is, it's really likely that the wave information will benefit the retrieval. Clearly, winds and waves are not completely correlated, and the winds can leak significantly. What do you think the status of the wind prediction will be by the time ODYSEA launches? Will it be sufficient to correct for wave effects at high resolutions? And what does high resolution mean?
All right. Okay. Let's. So first, what we should do about the surface and bound capillary waves, or where that is. Right. So I mean, I've seen some beautiful pictures of lab data with breaking waves, incipient breaking waves, and the train of capillary waves riding on top of that. And that certainly is a place where you may get these 4 millimeter waves that we're hunting for. But I mean, the way I'm taking it is, I really would like to get more spectra of very short waves. So there's some in-situ field data, a little bit from modulation of brightness of the surface from Eurosky et al., for example, from the platform in Cazzivelli. And I think we can try to generalize that to different sea state by maybe looking at not so much the brightness from optical imagery, but also polarimetry. So this is why I was breaking up these images. We actually have quite a few terabytes of data we acquired. We actually never fully analyzed because, well, we had other projects to do, and that was not really we're funded for. But so we have collocated stereo video data with polarimetric camera that resolves centimeter scale wavelengths. That may be still a bit longer compared to the waves we're looking for, but that's something I would really like to push for and see, how much we can see. The magnitude of these waves all over the place, like in the middle here, where there's certainly some roughness here, not just at the crest of longer waves, where there should be also. So that's my quick answer to that. I really don't know what the spectrum looks like and how these waves are distributed, spatially over the long waves, and that's something we need to have access to, not just the average spectrum, but the distribution of short waves with respect to long waves. And the answer to the other question, I think you're saying that we probably will need some more information in the future, and I guess your question was more on the quality of the wave models, not the wind models, right? Because the wind, presumably, we get it from the backscatter, although the backscatter also.
People like Leah have shown strong interactions to shears, fronts, and so on. Will we be able to, in a decade, will we be able to predict those well enough to be able to correct for some of these effects that you're talking about?
So there's two things. One is the large scale effects, which I believe are the kind of systematic deviation if we just look, for example, at Stokes rate as a function of wind speed and wave height. So that effect is probably large scale stuff, but it's only maybe 25% of the residual that we're interested in. And it's quite likely that, yes, the fact that the waves also feel the currents and the wave height and the different moments of the spectrum are modified by the currents. We're starting to see very nice current maps from SWOT, which is only part of the current. But the main idea of ODYSEA is to actually be the first missions to measure the current at high resolution and the full current that actually is causing this. So maybe it's going to be through simulated scenarios and neural network learning what should be the impact of these currents, and then be able to have some correction of possible biases in the GMF based on the current. So how we actually bring in the gradients in the currents onto correction for the Doppler. Of course, we won't have models that will resolve operationally the kind of scale that we'll be measuring. So we probably will have to rely on some canned or pre-computed scenarios or stuff like that of what kind of gradients would cause what kind of Stokes drift and what kind of variation in Doppler. That's maybe one way to go.
Well, thank you.
But SWOT data will be invaluable for looking at this kind of stuff.
Fabrice, while you have this figure up, I wondered, you said that the distribution around the center line in this figure is not just
Right.
random error. And
There's-
you've been talking about some of the things that might influence it. Is there seasonality in that distribution, or?
Oh, that's a very good question. Well, there will be there is some geographic variation for
Mhm.
sure. This is for station Papa, so I look at other buoys, not
Right.
based. Yeah, the cloud of points is a bit different. The median is going to be in different place,
Mhm.
for sure. And enclosed basins, short fetch is going to be pretty different from that. Basically, because the wave height you get are different, and then that will shift the whole thing. Yeah.
Mhm.
So I would expect that seasonality in there too.
So it seems like if there were a swell effect that had a really clear seasonality, that might be something that there'd be hope to deal with faster than the
Right.
wave current interactions.
Pure swell luckily has a very low Stokes drift because
Right,
it's
yeah.
very small steepness, so it's more a wave age thing than anything else. But
Yeah, and there's plenty of wave age variation in station Papa.
So the residual here of 2 centimeters per second is for that station and that 7-year. So if you do it season by season, you can probably reduce that to less. But of course, if you take it to a place, that will introduce more variation. So yeah, I should pull out my other.
That would be fun to look at.
Yeah.
Yeah. Momet has his hand up.
Yeah, since Ernesto asked a far ahead question, so for the time when ODYSEA will fly, doesn't this, if I understand your comment right, doesn't this call for something like an inverse of the complete solution? So right, you get a swell for any given pixel or any given location.
Yeah.
You get a swell information from a wave model, and then you have to propose an inverse problem, and then you ask for currents, waves, and winds at the same time.
Right. The thing is, that's not local problem, of course, because the current gradients will affect the wave height and the wave spectrum down wave of where the current gradients are. So it's more of a neighborhood thing. So yeah, it's just, you cannot do it point by point by saying, oh yeah, I know the current in this place, so I know the spectrum, and then I can invert that. So it's yeah. Yeah,
well, but it seems like you have to solve everything, like you have to solve all 3 quantities at once, at least in a semi-local framework.
Right.
Yeah.
And presumably there may be also small effects of the waves also on the backscatter, the sigma naught, which gives the wind in DopplerScatt ODYSEA.
Okay, thanks.
Other questions? I had one really small question, clarifying question. You did simulations and you said you had a 30-kilometer region.
Right. So basically, we generate a surface of 30 by 30 kilometer discretized at 3-meter resolution. We have typically 10,000 by 10,000 pixels, of which we use so far we're going to use a spatially uniform C state, so we just essentially generate the surface by making a sum of Fourier components, random phases, and then we compute at each of these small 3 by 3 meter facets the backscatter phase and amplitude of the radar signal, and then we sum all of that at the radar antenna to get the INQs, and we do then the full processing with a range compression and whatever the radar is supposed to do, and then we get the result. Yeah, that's what we do in sample simulation. So of course, right now our service is pretty dumb because it doesn't have any information of how the magnitude of the signal changes along the long wave profile, and also 3 meters is probably too big a facet to really look at the details of these modulations. But that's a starting point.
And then you can test that out, I guess, at arbitrary pixel size.
Right.
Potential
And
retrieval.
so presumably once we introduce more realistic things, yeah, we'll do that over smaller
Mhm.
areas where ideally it will look like the picture was showing before.
Mhm.
With all the small scale stuff, with the right shape of the waves, there are symmetries and all that. Yeah.
Mhm. Okay. Any other questions? I think there's a lot of food for thought here. But we may let people take additional questions offline and interrogate Fabrice via email. So,
Yeah, and yeah, sorry, it was Roland Romeiser names that I was slipping my mind. So thanks for Ernesto to correct that.
well, I'm going to stop recording.
All right.
And